Another set of trig identities that are beneficial to know are what are called the double angle identities. Now when you think of doubling something, it's like multiplying that by 2. So when they say they're the double angle identities, it's the trig function of 2 times an angle. And that can actually come in a lot of different forms when we get into more and more examples. Also, when you think about saying 2 times something, like if I say 2 times x, well that's just like 2 x's added together. So we can actually develop the double angle identities that I've already written on the board by going back to our identities on the sine of the sum of 2 angles, or the cosine of the sum of 2 angles, or the tangent of the sum of 2 angles. So let's look at that first, and we'll get these identities developed from that in case we ever forget the simplification, how we could get it back if we forget. And then we'll go and do some examples applying the double angle identities. So first of all, I have sine of 2 times alpha. So 2 times alpha is the angle that you're taking the sine of. And so since it's twice an angle, it's called a double angle identity. Now, when I look at this, I have to also make sure that I realize that you don't have any sort of rearrangement that you can do automatically, like pulling out numerical factors from in front of the angle and coming in front of the trig function. That doesn't work at all. There has to be where you look at what the expansion is and the simplification of the expansion so that you really have an equivalent expression in your identity. So for the sine of 2 times alpha, that's actually equal to 2 times the sine of alpha times the cosine of alpha. I need that entire expression to mean the same thing as the sine of 2 alpha. Now, how we can get this is we can go back to our sine of the sum of 2 angles, say sine of alpha plus beta. If you look at a previous video where it was the trig functions of the sum or difference of 2 angles as well as cofunctions, for the title of the video, it talks about the sine of the sum of 2 angles. The memory device for this is that with the sine of the sum of 2 angles, the SIGN between the terms matches what you did with the angles, but the trig functions don't. So this is going to be the sine of alpha cosine of beta plus the cosine of alpha times the sine of beta. And that's what we had for the sum of 2 angles. Now, what if the angles are exactly the same of each other? What if instead of the sine of alpha plus beta, it's the sine of alpha plus alpha? So I'm going to change all the betas to alpha to just make this generalization. Well, in the parentheses, alpha plus alpha is 2 alpha. So that's the sine of 2 times alpha is equal to, and over here I have the sine of alpha cosine of alpha plus the cosine of alpha sine of alpha. Well, multiplication is commutative. So I really have sine alpha cosine alpha in 2 different terms added together. So that's my 2 sine alpha cosine alpha that I originally wrote up as an identity. So if I know my sine of my sum of 2 angles, but I forget what the sine of twice an angle is, I can write out the formula for the sine of the sum of 2 angles, make both angles the same angle, and simplify them, and I will generate this identity back. Now cosine of 2 times an angle, so cosine of 2 times alpha, is cosine squared alpha minus sine squared alpha. We're going to do the same thing we did with the sine. So remember, for the cosine of the sum of 2 angles, the trig functions match, but the signs between don't. So I'm going to have cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. But then if I want to figure out what the trig identity is for the cosine of 2 times alpha, I'll make each angle alpha. So this is the cosine of alpha plus alpha is the cosine of alpha minus sine alpha sine alpha. Well, that's the cosine of alpha plus alpha is 2 alpha in the parentheses, and equals cosine alpha times cosine alpha. That's cosine alpha squared. But the convention is, instead of writing the parentheses with the square on the outside, is to tuck the square between the cosine and the alpha. So cosine alpha times cosine alpha is cosine squared alpha, then minus sine alpha times sine alpha is sine squared alpha. Now here I've left some space because there's actually 2 more forms of the cosine of twice an angle. And I just have to look at the other stuff that's going on in the problem to determine which of those 3 forms total for the cosine of twice an angle would get me to where I need to be in the process with whichever problem I'm working on. And why there's more forms for this one and there wasn't for the sine of twice an angle is because in the cosine of twice an angle, I've got cosine squared alpha in there, and I've got sine squared alpha in there. And we want to remember and kind of recall from our 8 fundamental trig identities, there were the Pythagorean identities there, and we have that cosine squared alpha plus sine squared alpha is equal to 1. Now this is minus and that's plus, so it's not a direct substitution into the entire thing. But not only do I have this form, if I take this fundamental trig identity of cosine squared alpha plus sine squared alpha is equal to 1, and subtract the sine squared alpha from both sides, this gives me that a cosine squared alpha replacement could be 1 minus sine squared alpha. Well, if I take this cosine squared alpha out and replace it with 1 minus sine squared alpha, I have cosine of 2 alpha could also be represented by 1 minus sine squared alpha minus sine squared alpha. But that's minus sine squared alpha minus another sine squared alpha, that's 1 minus 2 sine squared alpha. So I have that form of it, I have this form of it, and then you're probably saying to yourself, well, why did she solve that for cosine squared alpha? Why didn't she solve it for sine squared alpha? We could do that too. So if we take and subtract the cosine squared alpha from both sides of this original one, I would have sine squared alpha's replacement is 1 minus cosine squared alpha. So if I go back to this, one that's I originally generated, and take out the sine squared alpha and replace it with 1 minus cosine squared alpha, this gives me cosine 2 alpha could also be cosine squared alpha minus from the formula, and I'm replacing a 2-term expression in where a 1-term expression sat after a minus, so I have to put it in parentheses to make sure I subtract the entire expression that it's equivalent to. Well, when you distribute the negative sign through, the negative 1 through, negative times my 1 is negative 1, and negative times negative is a positive cosine squared alpha. So I get cosine of 2 alpha is equal to 2 cosine squared alpha minus 1. So there are 3 different trig identities for the cosine of twice an angle. And again, it depends on what's going on in the rest of the question to which of these that you would use. There's just one of the trig identities for the sine of twice an angle. Lastly, let's look at the tangent of twice an angle. Piece of it here because of developing the cosine of twice an angle. Let's develop this below it. So remember, the tangent of alpha plus beta is the tangent of alpha plus the tangent of beta over 1 minus the tangent of alpha times the tangent of beta. Now, remember, to get 2 alpha, we just change the betas to alphas. And I have tangent alpha plus tangent alpha. So when you're adding like terms, you have our 1 tangent alpha plus another tangent alpha is 2 tangent alpha for your numerator. But in the denominator, it's 1 minus tan alpha times tan alpha, which is tangent squared alpha. So that gives us our double angle identity for tangent. Next up, we're going to write out some different problems that ask you to utilize these double angle identities to make simplifications and also to prove and verify identity. Here are some examples of ways that we can use our double angle identities to simplify expressions or to actually find the values of trig functions of double angles if I know a trig function of the angle itself. So first one says, write 6 sine 7 theta cosine 7 theta in terms of a single trigonometric function. So with this one, I'm actually looking at this as, is it the output of the right-hand side of one of these identities? And if so, how do we pack it back to the left-hand side? So I see that it's sine an angle, cosine the same angle, and there's a coefficient in front of here. And these right-hand sides, the one that's closest to it is this one. With sine the angle, cosine the angle multiplied together, these angles are the same. They're 7 theta, takes the place of the alpha. But I need a coefficient of 2 in front of it, and this has a coefficient of 6. So I'm going to write this as 6 is 3 times 2 sine 7 theta cosine 7 theta. Now, this part of it right here is exactly this right-hand side with the alpha being the 7 theta. So if I bring it back to the left side, the 3 comes down, but then this is times the sine of 2 multiplied to whatever that angle was, and that angle was 7 theta. So then that's caught in the angle, so I have 3 times the sine of 14 theta. So that's utilization where I'm actually coming from the other side back to the left-hand side. Let's look at the next one. This says for cosine alpha being -3/5 and my alpha being in the span of angles from pi over 2 to pi, so that's the second quadrant, find the sine of 2 alpha, the sine of twice that angle, the cosine of twice that angle, and the tangent of twice that angle. Well, if I have my cosine of alpha is -3/5 and my alpha is a second quadrant angle, my reference angle, remember, comes to the nearest x-axis, and I have my motion is left 3 and then my hypotenuse is 5. And we'll use the Pythagorean theorem to find the missing side of the triangle. So y squared plus -3 squared is equal to 5 squared. And I get y squared is equal to 25 minus 9 is 16. Take the square root of both sides, y is plus or minus 4, but I have to go up to get into the span of angles from pi over 2 to pi. So that's going to be a +4. Now I want to go back to my identity. So the sine of twice an angle is 2 times the sine of that angle times the cosine of that angle. So it's 2 times the sine of alpha. Remember, here's my picture for alpha. I want to read the sine off of it, and sine is opposite over hypotenuse. So that's 4/5. And then times the cosine of alpha, and the cosine of alpha is adjacent over hypotenuse. So that's -3/5. So then when I take 2 over 1 times 4 over 5 times -3/5, that gives me my 2 times 4 is 8 times -3 is -24 over 1 times 5 is 5 times 5 is 25. So I have -24 over 25. Next up, the cosine of 2 alpha. Now this expansion with knowing I can get either of the values, I can use any of these three that I want to. Since the cosine of alpha is right here, and I want to maybe utilize that, I'll just go ahead and use this third one, but all the other two would give you exactly the same value. Any of them that you use, you'd get the same value. So the cosine of twice alpha is 2 times the square of the cosine of alpha. So the square of negative 3/5 and then minus 1. Now follow your order of operations. Negative 3/5 quantity squared is 9/25. So I have 2 times 9/25 minus 1. So that gives me 18/25 minus, get your common denominators, 25/25. And I get a negative 7/25. And if I were to, again, use any of these other ones, I'd get the same value. Lastly, tangent of 2 alpha. So the tangent of 2 alpha is equal to 2 times the tangent of alpha. So 2 times the tangent of this angle. So that's 4/-3. Divided by 1 minus the square of the tangent of alpha. So 1 minus the 4/-3 quantity squared. So remember, that's 2/1 times 4/-3. So that's 8/-3. And I can write that as negative 8/3 over 1 minus, and 4/-3 quantity squared is 16/9. Now again, in order to simplify this so I don't have those complex fractions, I look at all the denominators. I have a denominator of 3 and a denominator of 9. So my lowest common denominator through that is 9. I'll multiply the top by 9/1 and the bottom by 9/1. 9/1 is just 9. So I'm multiplying the top by 9 and the bottom by 9. So then I get my 3 goes into 9 3 times, and then times negative 8 is going to give me a negative 24 over, and this gives me 9 minus 16, which is negative 7. And then negative 24 over negative 7 is a positive 24/7. Now I want you also to recall that you can always double check with what you know with the trig identities from the 8 fundamental trig identities. Remember that the tangent of an angle is the sine of the angle over the cosine of the angle? Well, that's true for the expressions too. So the tangent of 2 alpha is going to be equal to the sine of 2 alpha divided by the cosine of 2 alpha. So if I take, for this particular question, it's all relating on alpha and asking twice alpha for that particular angle. The sine of 2 alpha was negative 24/25. The cosine of 2 alpha was negative 7/25. So when I take this negative 24/25, divide by negative 7/25, negative divided by negative is positive. When you flip and multiply, the 25s will cancel, and you'll get 24/7. Quick way to see if you did your arithmetic right, just double checking, and then also continually reviewing the 8 fundamental trig identities, reminding yourself of what each of these things are equal to, so that you are able to keep reinforcing it and get a stronger foundation when you need to use it later.